Hello everyone. In this workshop, I am going to present the method to apply 3D velocity profile in the pipe using expressions. So without UDF, we can still apply the customized boundary conditions in Fluent. And in some previous workshops, if you take a look on the previous workshop, you can see that we have applied this UDF for 3D case. And the equation we used is this one, that the U is equal to U maximum into 1 minus R square upon R square. Okay, but the problem is that if you take a look here, that we have to define the radius by ourselves, and although we can get the radius from the area and then divided by pi, but the issue is that in the UDF terms, we had to write down the program, and it was a very lengthy programming to get the area for some surface. So I didn't want to include that much part in the UDFs because this will be a complex and cumbersome. So that's why I defined the radius directly here. But if you take a look here, in the case of expression, this is very much simple. So I can get the radius of the pipe, that is from here to here, by simply getting the area function, using function in the expression at the inlet, and then divided by the pi. Okay, so you know that the area of circle is equal to pi r square. So from here, basically, we can see that the r would be equal to area upon pi. This will be square root. Okay, so by applying this thing, we can have the area, the radius. And second thing is the radius, local radius is x square plus y square, and the mean velocity is 1 meter per second, and velocity profile is defined by this equation which is given here. And then you can see that we have the parabolic velocity profile in all directions. Okay, so now let's start with this case in the Fluent. And I'm using the previous workbench file, and I will just replace the UDF with the expression. So I will not make the geometry or meshing this part. So you can go to 3D velocity profile using UDF. The geometry part and the meshing part is exactly same, which is I'm going to use over here. Okay, so I'm going to right click here, and I will be duplicating this whole cell here, whole container. And so this is a file which is basically I'm going to attach with the first lecture of this section. This is only one lecture, so you can see there is the downloadable resources, and you can download the file, and also this slide here. Okay, I just made a small change, although the area was around 1 meter square. So using the area of inlet divided pi and square root, so this should give you the proper value of radius r. So I didn't include the square root in the function because this was giving me the same area, but it should be used like this. Okay, so this is duplicated, so I'm going to reset the whole setup. So right click here and reset. Okay, so I want to keep the same geometry and the mesh, but I want to update the setup part. So double click here, and I will start from the scratch. Okay, so let me open the that file which we used for this UDF. So I think the material properties were exactly the same. Okay. So material properties are exactly same which we used in the 2D case. So this is exactly same thing. So we have the pipe. Actually for this case, the properties are a little bit different. So density is taken as 2.5 kilogram per meter cube, and the U mean is 1 meter per second. And diameter this time is not 0.1 but not 0.2 but 2 meters, and pipe length is 20 meters. Okay, Reynolds number is kept as a 500, so from here you can find out the viscosity to be 0.01. Okay, so let me close everything, and I want to open the things again fresh. So from setup, double click here, and I would be putting the properties like this. Okay, so these are properties. Density, diameter is already there in the geometry, and density is 2.5 kilogram per meter cube. Velocity is 1 meter per second, and fourth thing is the viscosity, which is 0.01 calculated from Reynolds number. Okay, so still we will keep the flow as laminar. So it's double precision, 4 cores this time. And the mesh is kept with a very less number of cells to just demonstrate the velocity profile using expressions. So the number of nodes are 43,531. Okay, there is the warning. This is double precision solver, no problem. So this is the inlet, blue color, and outlet is in the red color. These are default colors, and for wall the color is gray. Okay, you can display the mesh also in this way. So boundary layer was made with intention to have the more grading towards wall, so that we can resolve the boundary layer properly. And wall has a decent mesh spacing along the length. And if you take a look on the quality, this quality is 0.86. So minimum orthogonal quality is 0.86, and that is almost equal to the best quality, because best quality is a 1 and 0 is a worst. So it's almost close to the best quality. And the aspect ratio is 36, which is also good. It should be less than 100. Okay, so in the models, I will be changing the turbulence model from SST to the laminar flow only. And in the materials, I will change the properties for density and viscosity to 2.5 and 0.01. Okay, 0.01 and 2.5. Click on change, create, and close. And in the boundary conditions, right now I will just check the boundary conditions, because I will be coming back here, and I will define the boundary condition for inlet by expressions. So outlet should be outlet, wall, and velocity inlet. Okay, and so now the next thing is that the name expression. So right click here and click on new. So you can exactly copy these values. So you can see the format. So you can even type this whole thing inside the Fluent. So I will be making them side by side like this. Okay. And I will zoom the particular area. So first the radius R. Okay. This radius R is the capillary radius, which is the radius of the whole pipe, which is equal to 2 meters. Okay, so it's a 0.1. The 2 meter is a diameter, radius would be equal to 0.1, is equal to 1 meter. So diameter is a 2 meter, radius would be equal to 1 meter. So this is going to be the first. I will start with the area. This is much easier. So we have the okay 1 minute. Okay, area. And where we want, so just delete everything inside and go to locations and click on boundary zone and surfaces. Inlet is the area where I want to inlet is a boundary condition where I want to have the area. So it's the area, and if we divide by the pi, so this will be the r square. So this will give us the r square, because area is equal to pi r square. So if we divide by the pi, this will give you the r square value. So constants is the pi, and now I'm going to use a function that is the square root. So from the mathematical square root, and it should be inside the bracket. So what I'm going to do is that I'm going to delete everything inside the bracket, and then I will be cutting this thing from here. Right click here, cut, and paste inside. Okay, and to confirm this thing, this should not give you any error at all. Okay, sometimes this does not try to give you the proper area, but it should give you the radius value, but no problem. So we will work with it. Close this thing, and you will see that we have a new name expression, that is the radius r. Maybe we can try now. Okay, now this is giving us the radius which is almost equal to 1 meter. Okay, so close, and here right click here and new. So this is going to be the local radius, which is local radius is a r. So r is a local radius along the any point, at any point. This is equal to under root x square plus y square. So I'm going to use again the expression, that is the square root, and inside the bracket this is the x square plus y square. That's all, and press enter key, and it should not give you any warning or error. So everything is all right. So this is the radius small r. Okay, so click on OK, and if you go back again, this should give you something here. So expression is not available to single value because this is varying with the different x and y values. That's why we're not getting any single value, but you can plot it if you want to plot it. Okay. Okay, third thing is the mean velocity. So this is the u mean, and its value is 1 meter per second. So you must mention the unit as well. So 1, and in the square bracket this is a 1 meter per second. So if there's some error in the unit definition, this should give you the idea. Okay, so okay, and go back again. So 1 meter per second. Okay, also you can write down this thing as without this division sign, and you can put the power like this, the power sign and the -1. You can also try this operation and see what happens. So again, okay, go back and check. Okay, so same thing here. So it automatically converted the unit to the meter per second. So you can also define with the power on the second as a -1. Okay, close, and the last expression is the expression for the velocity profile. That is the u maximum. This u maximum will be equal to twice a u mean. So 2 into u mean. So you can choose now expressions, u mean, and into, so bracket starts 1 minus, now again bracket starts, this is a 1 minus r square upon r square. So expression of small r square, and then divided by again the new bracket. So this is going to be the, so I'm going to put the two brackets. So one is a bracket for the local thing, and one bracket is for the everything, that is equal to r square upon r square. So again I will be putting the expression, that is a capital R and square. So bracket close for the local function radius r, and then a bracket close for this whole function, that is r square upon r square, and then I will close the bracket for this bracket which is before the 1. So third bracket is over here. Okay, press enter key, and you should not be seeing any error or even any unit problem. So everything is all right, and you can click on OK. Okay, now in the boundary condition I will go to the inlet, and from here I am going to choose for the velocity magnitude as the 1 minute. So this is the expression 1. This is the velocity profile. Okay, velocity profile, and now look for the velocity profile. This should be somewhere here. So you can again close and open it again. So velocity profile. Okay, you can save the file, save the project. Okay, so after saving, now again double click on inlet and see we have the velocity profile. So click on apply and close. So now in the methods, I will keep the default setting for coupled solver, and in the monitors, I will be putting the more zeros here. So 10 power minus maybe 20. For 3D case, we get the unlike the 2D cases where we get the convergence up to 10 power minus 20, but in the 2D cases, it is almost limited to 10 power minus 10. So this is a good value. And now initialize from the inlet. Okay, initialize and run calculation for around maybe 300 iterations. So I will keep the 500 iterations and click on calculate. And here you can see that the solution has been stopped after 500 iterations, and it looks like solution was converged within 150 iterations. And this is the benefit of coupled solver. All right. So now from the results, I'm going to display the velocity profiles at inlet and outlet first. So you can see this is parabolic velocity profile, and the value of velocity is varying from 1 to 1.97. So same is for the outlet, and if you make it banded, so you can have the like 30 color maps and make it BGR, blue, red and green. So this will give you the better idea. Okay, now you can create the mid planes, so at different locations between inlet and outlet. So I'm going to use the mesh and Z coordinate. So I can first create here, second one we can create for example here, third one here, fourth one maybe here, and also here. So 5 planes are okay. So I will use these 5 planes and display velocity profiles. So they are exactly same. They are exactly same. Okay, you can also change the color map to let's say 250 and see the difference. You can also make it a smooth one, and let's say you make them as 100. And if you change to the arrow, you can see the color map will look like in this way. And if you go back to the original one, that is the variable, I think, velocity. Field velocity, yes. So this is like this. Okay, and at the same time, you can also display the outer part of your geometry. So this will be now much better. Okay, similarly, I can create a line along the, let's say, along the y-axis. So let's create a line along the y-axis. So let's say we create line at 18 meter per at the 18 meters. Pipe length is 20 meters. I'm going to create line at z is equal to 18. So both values of z will be 18, and the radius is 1. So -1 to +1. Create, and if you want to display the mesh, the dead line, so you can see the line is over here. Line is over here. So let's say I don't display the wall. Line is here, and maybe we can change the colors, and we can still line. Okay, also with the faces. Okay, so here line is here. So on this vertical line, I'm going to display the velocity profile. So from the XY plot and the position on the y-axis. So this should be along the y-axis, the length one. So, and I'm going to display the velocity, and we are line number 8. So this is over here. Okay, and also you can change the color of the curve, so you can also include the line like this. You can change the size to the, let's say, to the 0.5, and you can also change the line width to, let's say, to 3 or maybe 5, whatever is suitable to you. So, and we can also change the color of the line and as well as the color of the these marker dots. Okay, so this is the velocity profile and it shows the parabolic velocity profile, and the this is not refined on the midsection because that the mesh is very coarse in the midsection, but it is very fine in the boundary layer. That's why you can see the more points on the line but less points in the middle section. So you can include the more cells in the middle section as well to resolve this line in a proper way. It will take the proper curvature of parabola. Okay, so with this, now we are ending the workshop, and so in this workshop, basically you learned that how to apply the 3D parabolic velocity profile in a pipe using expression instead of the UDF. So we have gone through these functions for the radius R, and the U mean and the velocity profile.